go into linear spaces and maps and some of the transforms we're going to look at for the rest of the chapter. So this was your example to work out. First row dotted with the first column. Straightforward. Gives us a value of 10. Okay, put that up in the right place. Now you might have done this in the Tableau format where everything's lined up vertically. That actually is fine. It's just easier to fit all this on the slide. So get going. We do the second row times the first column. Do all the pairwise multiplies or dot product, get -1, and then just running through. Whoops, a little too fast there. We get our final answer here. If you had any problems with that, each of the slides had the full math. Make sure you just didn't do a simple math error. If you understand the concepts, you had an algebra error, you're going to have to work on that a little bit. Hopefully everyone did it straightforward. If you had any problem with that in terms of conceptual, you better go watch those Khan videos so get a little more practice. Okay, so now let's move on to the more interesting part of this chapter, linear spaces. 2D linear maps act on linear vectors in 2D to map them to other vectors. Okay, this is called a vector space. And an important property of why this is called linear algebra and linear spaces is that these are linear operators. We call that because we can take some scalar, vector 1 times a1 plus vector times a2, and we get some new vector, and it preserves the properties of linear combinations. So if I take some scalar a times vector u plus b times vector u, and I multiply that, I do those scalar multiples with vectors, add them together and multiply by a, matrix A, I'm going to get the scalar a times the matrix A times u plus b times the matrix A times u. So I can associate those in different ways. This really means that we can treat lots of things in a nice forward fashion, and we can deal with scalar multiplication in addition, and then we can do with vector and matrix multiplication in addition, and we don't have to work out a lot of that. Sort of see how this works sort of algebraically as well as graphically. Let's look at an example. So let's imagine that I have two vectors. U is 1, 2, and V is -1, 4. So here's our U. Where's V? V is -1, 4. So V goes this way. But we're just going to draw a U for a second. If I look at what is this matrix A here, which is -1, 1/2, 0, 1/2, if I multiply A times C times U, I'll see that that's the same as C times A times U, and I can just let, say, for example, C equals 2, work out the example, and you'll get that that's equal to 2, 0 minus 2. So if I take this and I double its length, and then multiply by the matrix A, which brings it down here, that's the same as taking this matrix, multiplying it by A, and then scaling it. And those orders are the same. If you wanted to prove this in a general sense, you'd actually do all this with algebra and show that you'd get the same constant. So you'd make a matrix with like A, B, C, D, you'd make U into E, F, and then you'd have some constant down here, and you'd work it all out and show that algebraically they're the same. But intuitively, this is just showing that I can change the order of scalars and multiplies. And in general, linear spaces preserve another important thing, that is this distributive law. So A times U plus V is the same as A times U plus A times V. And again, we can sort of think of that diagrammatically. When I have U plus V, that gives me this vector here, and I can apply the matrix A to it, which might bring me down here. And I could also apply A to V and A to U, and then when I go to combine them, I'm going to get the same set of final answer. See this again in terms of overall for a full combination. A times 3U plus 2V. Or again, I'm going to use the same A, U, and V we had before. So here's A. 3 times U plus 2 times V. If I do this part first, I get a total of 6/7. If I take it and I take first the matrix and I multiply it by each of these, so I take 3AU. So here's 3AU plus 2AV, and I do this matrix vector product times that, or if I do it in the other order, it doesn't matter, I'm still going to get 6/7. Okay, so linear spaces preserve linear combinations. I can do these operations in a lot of order. Okay, so as long as I distribute and associate those things, I'll be okay. Okay, so now let's look at what these matrices are. This is actually where it starts to become a little bit more interesting. It's not just they have this nice properties, but we can talk about very special matrices. So if I have a vector v, and I scale it and multiply it by a matrix, in this case, oh, that's a v prime, sorry, that should be an a. If I multiply it by this matrix A, I'll get a v prime. Oh, I see. Yeah, so this is the matrix A, here's v. A times v prime gives us v1 over and v2 over 2. That is this matrix, 1/2 on the diagonals and zeros on the off diagonals, is a scaling matrix that scales everything down by a factor of 2, so shrink them all down. Okay, I can actually do a general scaling. The general scaling matrix looks like a value S11 and S22 and zeros on the two sides, and that will scale it by S11 in the E1 direction and a factor of S22 in the vertical direction. So this is sometimes called an action ellipse because the action of this matrix is to map what was a circle into an ellipse. This is a special ellipse, it's either vertical or horizontal, but this matrix is mapping those things and changing their shape. If they're both equal, so as we saw with 1/2, 1/2, it's a very special ellipse. It's the ellipse we call a circle, and it just scaled everything down, so it maps a circle to a circle. Okay. So matrices can do other things. They can do a very special scaling, which we call a reflection. So if I scale this axis by 1 and this axis by -1, well, scaling by -1 sort of changes direction, and so what ends up happening is we take this shape and we flip it over the horizontal, or we flip it over the vertical axis, so we change its horizontal scaling, and we get this shape. Okay. No, sorry, actually, we flipped it over the horizontal line, and we get this shape. Right, so it's minus v2, the second component. Okay, so reflection maps each vector around a line through the origin, and in this case, it's the horizontal axis that it's going to flip over. Okay, we can actually flip around the other axis. If we can flip around a general line, y1 equals x1, so the line that goes like this, that reflection looks like 0, 1, 1, 0. Okay, and that really just swaps the x and y values. Think about multiplying by this. This is going to take the second component of v and move it up, and the second element takes the top component of v and moves it down. So I can reflect about a horizontal axis, the vertical axis, by using plus or minus ones. I can also flip around the diagonal axis. Okay, and so effectively rotation here is still a change of the sign of the area of the orientation of this. So if I actually ask about the sign of the area, which we'll talk about in a little bit, we'll get more complicated areas. We'll get negative areas because of the way we've done this piece. So what's the action of this? Well, the action of this is still a circle. If I want to take this vector times that, I'm going to see that this is really the same as a rotation of 180 degrees. Right? So I have -1 and -1. I flipped horizontally and vertically. With two of those, I actually made the area negative, then I made the area positive, and in doing so, I also did the equivalent in this case of a 180-degree rotation. So all of these are very special matrices. In fact, they're a special case of an overall thing we call rotation. So if I want to build a rotation matrix that rotates E1 and E2 around the origin, so I want to take these two vectors and rotate them so E1 goes up here, and E2, because it's still at 90 degrees from it, is going to go over here. We can define that if we look at what happens. I was at E1, where do I want it to go? Well, I want to go up by alpha. I can build my right triangle, and I can see that the new coordinates for E1 prime are cosine alpha, sine alpha, because sine here is opposite over adjacent, cosine is, sine is adjacent over hypotenuse, cosine is opposite over hypotenuse. The two hypotenuse elements can be canceled out, and so I get that this is cosine alpha, sine alpha. E2, which was up here, is going to move over here, and that location will be minus sine alpha, cosine alpha, assuming that these, because these were unit length, so when I move them over here, that's what I'm going to move to. Now, we can actually take those two axes and figure out how to build a transformation, a linear map using them, because if we map E1 and E2, they tell us what we need to map. So we just build this matrix, cosine alpha, sine alpha, how we moved E1, how we moved E2, minus sine alpha, cosine alpha, and that gives us a transformation matrix. And fill in different values for alpha, and this will tell us how to rotate by 45 degrees. We just put in alpha equals 45 degrees, and that puts in this rotation matrix, square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, square root of 2 over 2. Notice that if I had this same thing and I multiplied them all by 2, I could rotate, but I'd also have changed scale. Rotations don't change areas. Their action ellipse is a circle. It maps circles to circles. They just have been rotated as they're going to be. Rotations are a special class of transformations called rigid body motions. They're also called orthogonal transformations, and they have a bunch of other special properties. We'll talk about those more later in the semester. Let's look at some other transformations, though. It's not just that we can do rigid body things where we rotate or flip. We can look and do some other things. What would happen if I wanted to map and I say, well, I want to leave E1 alone, but I want to make E2 move over here. Okay, this is what we call a shear. We're going to map a rectangle to a parallelogram. And when we do that, we're going to say we want 0, 1 to go to D1, 1. And if I think about what this does, the first column of my transformation matrix is 1, 0, because I want to map 1, 0 to 1, 0. I don't move it. The second axis is going to map, I want to map 0, 1 to D1. So that becomes the second column of my matrix, and this is my shear matrix, which will map 0, 1 to D1. If you actually put in 1, 0, you'll see it maps 1, 0 to 1, 0. So this builds an example of how to get a shear given that I want to map these two to these two. Okay, see what a shear looks like graphically applied to a more complicated shape. Here's a shear applied to the shape, which has got a bunch of different vectors, obviously drawing all that shape out. If I want to shear along an arbitrary axis, I can do that by sort of rotating, shearing, and rotating back. Okay, so here's a shear along the E1 axis. Here's a shear along the E2 axis. Go back. Notice the shear on the E1 axis has this extra term on the vertical. Shearing on the along the E2 axis has this extra term on the second item. Right? And that really just comes because we're multiplying this matrix out. Okay, so now we can ask some kinds of questions. What we often want to do sometimes is figure out what will get us there. So let's say I have V equals V1, V2, and I want to shear that so that I get V prime equals V1, 0. What shear will do that for us? Well, what we really want to do is we want to shear it along parallel to the E2 axis until this second element becomes 0. And so the second element, I want to shear this element down to 0. So I'm going to have 1 minus V2 over V1, and then 1, 0. And why does this work? Well, because when I multiply this by V1, V2, the second element becomes, we multiply this out, and then we'll get the right shear. Note that shears don't change area. If we look at the parallelogram that we had sketched out here, right, the length of this is still the same, the length of that is the same, we're just shearing them along the axis, so they don't actually change area. The rectangle has the same base and height. If you break it up into triangles and put it back together, you'll see it didn't change the area. So in terms of general operations, the next one to talk about is a projection. This is a very special case because now we're going to take a parallel projection. We're going to take the vectors and project them. We've already talked a little bit about this. There are other kinds of projections called perspective projections, in which case the result is no longer, the direction isn't constant. It produces, it does not produce a linear map, and to do projections, which we'll talk about more when we get to 3D, perspective projections, we'll have to add some other elements to get there. But orthogonal projections, the incident angle is 90 degrees, or parallel projections, these projections will retain everything. Now, this simple class of orthogonal projections is still useful because it's a way for us to get the best approximation. And it has lots of applications fields, computer architecture, computer graphics architecture, computer vision. And the main property of a projection is that it reduces dimensionality. I used to have this complicated 2D shape. Now I have a 1D line, and it sort of represents some of it. And the action ellipse of this is a straight line segment which is covered twice. We sort of go there and back again because we go around a circle, map a circle into the, basically into the diameter of the circle. So how do we build a projection? Well, we want to choose some unit vector, and we want to project onto that So if I have U and I want to project onto this, so I'm going to define the first matrix A, the first column of my matrix A, to be such that U dot E1 divided by magnitude of U2 squared times U, right? That's what I'm going to define A1. Why? Because what I want to do is I want to take the E1 vector and I want to project it onto U. And if I build the right triangles, right, what is the length of this piece here, okay, the magnitude of U, and I do all the similar triangles, and this gives me the first element of my column, U1 times U. The second element, sorry about that, the second element, U dot E2 times the projection, divided by the magnitude of U times U, gives us this value of U2. Okay, so this matrix now will project any vector onto the vector U. Okay, notice that this matrix, although we derived it by looking at it in terms of the dot products and the triangles that might come down here, this matrix has a very special form. You can actually get it by taking U transpose. Notice we're right multiplying by U transpose here. So given any arbitrary vector, if I want to compute the matrix that will give me the projection, orthogonal projection onto that vector, I simply compute U transpose for the vector U. Okay, so that actually makes it pretty easy. Now, it is also clear, since that's our projection matrix, that it's really defined by one vector, not two-dimensional vector. It's whatever U is times U transpose. So the columns of A are linearly dependent. They have rank 1. And this map reduces dimensionality. The area in 2D, after I project things onto a line, is a line. The area of a line is 0. Okay. Projection matrices also have an important property called they're omnipotent. Okay. And that basically means you can apply them and they don't change. Once you've projected onto a line, projecting onto that line again doesn't change anything because it's already on the line, so it projects to the same. So now if I wanted to give this, given an example vector U, computing the matrix that gives us the projection onto U is actually easy now. We just remember this formula U transpose, and you just take this vector, 1 over square root of 2 times 1 over square root of 2, make a column, a row vector, which is U transpose, 1 over square root of 2, 1 over square root of 2. I multiply those out, and I get a 2 by 2 matrix. Remember, I'm taking a 1 by 2, a 2 by 1 times a 1 by 2, so the resulting product is a 2 by 2. If you write this out in Tableau form, that'll become more obvious to you. They actually only intersect once, and you just get 0.5, 0.5, 0.5, 0.5. That is our matrix that will project onto that. So the action of projection matrix on a vector, again, since I know that A is equal to U transpose X, I can also see that this is U times U dot X, and that's the way we saw orthogonal projections in Chapter 2. The nice thing about this formulation, as we'll see later, is this actually generalizes into higher dimensions and other objects. So if I want to think about Y being projected onto X and then onto U, so notice now I'm talking about let Y be the projection of X onto U. Then I know that X is equal to Y plus Y perpendicular, and I can solve for that. AX equals U transpose Y plus U transpose Y perpendicular. Since U transpose Y equals the magnitude of Y, and since U transpose Y perpendicular is 0, why is U transpose Y perpendicular? Oh, well, because we assumed it's projected, the projection of X onto U, so this is the point, this perpendicular, so its dot product here is going to be 0. We see that AX equals the magnitude of Y times U. So I also can relate the projection of X onto it, and I can estimate its size without even figuring out what is A. I get that the magnitude Y, if the magnitude will be, the magnitude of Y times U will be the projection. Okay, so now we've talked a little bit about area, so now let's try and make this a little bit more formal and give you some equations to help you model that and some diagrams to help you understand it. So a linear map takes the unit square E1, E2 into some new set of vectors A1, A2. And so we can ask the question, what does a linear map do to the area? Since the area of the original thing is a square, it's a unit square, spanned by these two things. After transformation, I'm going to have some parallelogram, which might be degenerate and just be a line, but I'll have a parallelogram spanned by A1 and A2. And I can think of that full parallelogram, and the area of that is 2 times the area of the triangle that is the triangle from the origin to A1 to A2 and back to the origin. So what's the area of that triangle? Well, the area of that triangle is simply A1, 1 times A2, 2. This side times that side, right, which is really, I'm taking the area of this square, minus the area of this triangle, T1, minus the area of that triangle, T2, minus the area of that triangle. Notice all 3 of the triangles, T1, T2, and T3 are right triangles, and so I can resolve them. In fact, I can resolve them whatever, getting into full sines and cosines. The area of T1 is 1/2 A11 times A21. T2 is 1/2 this quantity, A11 minus A21 times A22 minus A21. Similarly, T3 is obtained by just looking at the geometry. It's 1/2 of A21, which is this side, times A22, right? And that's just because if I move all of these, the 1/2 becomes, I'm really looking at what's the rectangle, and then recognizing the triangle is only half of it. So I'm just looking at each of those rectangles, saying, oh, the triangle bisects it, and that gives me all of these formulas. So overall, since P was 2 times T, it's A11 times A22 minus A21 times A12 times A21. Right? So that gives us what's the overall area after projection. So the signed, if we consider P to be the signed area of the parallelogram, and what do we mean by the signed area? Well, if the parallelogram swapped left and right, then if A21 was on this side, if A1 was on this side of A2, it had a flip, then we'll call it a negative area. And we can actually say that this is what we call this the determinant of A. And the notation for this is either the det of A or single vertical bar of A, which looks a lot like the absolute value of A, but in linear algebra, we don't take the absolute value of a matrix, we take the determinant of a matrix. And for a 2x2 matrix, we actually just derived what it is algebraically. It's A11, A22 minus A21 times A12. Okay, we're going to see the determinant again when we get to higher dimensions. It becomes a little bit more complicated, but the nice thing about this is it tells us a lot just by looking at that determinant. You should be able to answer questions. If the determinant is 1, then the linear map does not change the area of the map. If A is less than 1, the determinant of A is less than 1, then the map shrinks the area. If the determinant of A is equal to 0, the matrix is rank deficient and it shrinks the area down to 0. In fact, when you say it's less than 1, it shrinks the area by whatever the determinant of A is. If the determinant is greater than 1, it expands the area by the amount of determinant of A. And if the determinant of A is less than 0, then the linear map changes the orientation of objects. Okay, so if it's between 0 and 1, it shrinks. If it's between 0 and -1, what does it do? Well, it flips and shrinks. If it's less than -1, what does it do? Well, then it flips and expands. So we can take these examples here, just see a couple of examples of the determinant in process. So this matrix 1, 5, 0, 1 has a determinant 1, 1. The product of these minus the product of those. 1, 1 minus 5, 0 gives us 1. Here's another one. Again, it's a little bit like a cross. I'm going to take these two, 1 minus 1, minus those two, 0, 0, and I get -1. Here I'm going to take one that's got 0.5 times minus 0.5 times 0.5 is 0. This actually might be a matrix you saw when we projected onto the perpendicular line. This gives us that, and it's also clear. I projected onto a line. I get determinant 0. Okay. Now, since the determinant's an area, we actually expect to do some very important things. If I multiply by a scalar, right? So if one of the columns of A is scaled by C, then the determinant is scaled by c. So I'm not going to multiply everything. I'm going to take c times a1, and I'll see that's the c times the determinant of this. So it's not quite multiplying the whole matrix. And you can sort of see that because if I have a1, a2, and I have some area, when I take 2 times a1, I get twice this side, but I keep that side the same. So what's going to happen if I multiply both elements, both a1 and a2 by c? Well, if I multiply both c times a1 and c times a2, that's going to be equal to c squared times the determinant. And you can again see that from graphically. If I had this side, a1, and I multiply it by half, and a2, and I multiply it by half, this area is 1/4 of the area. And so the reason for that is, if you think about it geometrically, I'm multiplying each column by a constant, and now I'm going to use those columns when I go to make the area, so I get the square of them in 2D. So determinants are not linear in terms of how you multiply. If I multiply the matrix by a constant, if I multiply the matrix by a constant, then it's the same as multiplying each column by a constant. The determinant goes up by the square of that. So if I think about the signs of areas, we can also think about this in terms of left-handed and right-handedness in physics and the kinds of things you've seen before. So two vectors whose determinant is positive are called right-handed. So a1 to a2, and we call this right-handed because if you were to make your hand first move at a1 and then close your fingers, you'd move to a2 with your right hand if your thumb is pointing up. And we call vectors whose determinants, or whose 2D vectors whose determinants are negative, left-handed, because if I put my fingers pointing towards a1, I put my hand and I want to close my fingers and make it go to a2, and my thumb is pointing up, I have to be using a2. Okay, so that's why it's called left-handed. And the areas change sign. Okay, so I can go from left-handed to right-handed when columns are interchanged. So if I have these two matrix a1, a2, and I swap it to be a2, a1, then the determinant is going to change its sign. And if you just think about these two vectors, swap them, and if I want to go from here to here with my hand, with my thumb pointing up, and I change their order, then I have to change my hand to make it work out. And again, you can go back to the formal definitions of the algebra and make it all work out. So what happens when we start looking at determinants and more complicated things? Composing products. First, let's just talk about what we mean by composing. So I have some vector v prime, which I get by a times v. I can now think of taking a second matrix b, and I can apply b to v prime. That gives me a new vector v double prime. But that's the same as providing b to av, which I can view as ba times v, which is some other matrix C. That's the composite matrix. Okay, and the elements of Cij are just the dot products of the ith row and the jth column. That is to say, C is the product of A and B, and that gives me a new linear map. So if I take two matrices and I multiply them, and I apply that to a vector, I get the same as having taken the vector, apply the first matrix, then apply the second matrix. So let's see this as an example. So let's say I have v1, v2, v1 is 2 minus 1, our matrix A minus 1, 2, 0, 3, and the matrix B 0, minus 2, minus 3, and 1. If I were to take A prime, or V, if I were to look at V prime, which is AV, that's the same as looking at minus 1, 2, 0, 3 times this, which is 4, 3. If I look at taking that vector V prime and multiplying it out for V double prime, I'm going to take minus 0, minus 2, minus 3, 1 times minus 3, 4, and I get 6, 9. If I first compute the product of B times A, I get a new matrix, 0, minus 6, 3, minus 3, and with just a little bit of algebra, you can verify that if I multiply this times V, I'm going to get 6, 9. Okay, so composing linear maps, or a composite map, basically says I can take a bunch of matrices and multiply them all together and then apply them to a vector. Although here we're in simple 2D, this idea gets very useful when we start looking at doing lots of complicated transformations in very complicated graphic spaces, because if I first want to move an object here and then there and then here, because I've done local coordinate systems that nest multiple objects together, this says I can take all of the matrices that do all that compositing, put them all together, and then apply them to the vector once, instead of doing lots of vector matrix products. Okay, now one of the things that's important to remember with linear maps, though, is that because it's the same as matrix multiplication, it's not commutative. If I take this shape, okay, and I rotate it by 120 degrees, so I'm going to rotate by 120 degrees, and then I flip it around the vertical axis, right? That's not the same as if I first reflect it and then rotate it. Okay, so if you think of matrices here as rotations and flips and whatever, they're not the same. The order matters when I rotate and then flip. Now, that's not to say that all of them are the same. If I were to rotate by 10 degrees and then rotate by 20 degrees, right, that's the same as rotating by 20 degrees then by 10 degrees. The fact that sometimes you can commute doesn't mean all the time you can commute. So in this case, as soon as there's one example where you can't commute, it's not commutative. And that's, algebraically, we say that AB is not the same as BA. And so you can easily convince yourself, if you take a bunch of these, work them out graphically, you can sort of quickly see why rotating and flipping is not going to be the same. Okay. A couple of other properties of composite maps. If I look at the rank of A times B, well, the rank of A times B is the minimum of the rank of A and the rank of B. Okay, it's not the product of the ranks, it's not the sum of the ranks, it's the minimum of the ranks. Matrix multiplication doesn't increase the rank. There are some very special compositions, which we call omnipotent matrices. So if a matrix A has the property that it's equal to A times A, or A equals A squared, or AV equals AAV, this matrix is called omnipotent. And we know that certain matrices have this category. For example, the identity matrix does. But have we seen any other matrices that do? What matrix, when multiplied by itself, gives you back itself? Anything else? So how about rotations? Right. Well, some rotations might be. So if I rotate by 360 degrees and I do it again, it's not going to change. But not all of them are. Okay. Another property for matrix multiplication, just to put this back into context, we have a little bit more to cover there. If I take a matrix AB and I ask about its transpose, so if I take the product AB and the composite map, the transpose of that is B transpose A transpose. And if you were, say, on an exam or quiz asked to prove this, okay, to prove this doesn't mean to show that it's true for one example. To prove that it's true would show algebraically, work this out, write out what does C1 look like, work this out, show what does C1 look like, and show that C1, 1, C2, 1, C2, 1, 2, and 2, C2, 2 are all the same. Okay, and it's not hard to show this, it's just a little bit cumbersome to show it all out. But in doing this, you'll also see that here we have A11 times B11, A12 times B21. That's what we're going to make C1. But we're going to remember we have to take the transpose when we get done. So you can then show that those two products and these two products after transposing give us back the same form, just form C21, and so on for each of them. Okay. What about the determinant of a product? Well, the determinant of the product of two matrices, A and B, is the determinant of the matrix A times the determinant of the matrix B. Okay. Notice this also tells you the rank. Why is the rank going to be? Because the rank is, for a 2 by 2 matrix, if one of these is degenerate, what is its determinant? Its determinant is going to be 0 if one of these is degenerate. So B scales a matrix, scales an object by the determinant of B, and A scales the matrix by the determinant of A. So when I go to composite them, I first scale it by A, and then I scale it by B. So if I have two scaling matrices, this A is going to scale down by half, and B is going to scale up by 4. And I multiply these two out. What is the product of these two matrices going to look like? Well, it's going to look like 2, 0, 0, 2, which scales up because, remember, the two 2's end up scaling this column by 2 and this column by 2, so the determinant is actually scaled up by 4. And so you can just look at some of these properties and quickly figure out what's going to happen roughly to a shape. Another useful rule in the more general case is not just for multiplying things twice. So if I take A times itself R times, what's going to happen to its determinant? Well, it's just the determinant R times. So that's the determinant raised to the power R. Okay. Some other special properties which, again, are easy to show. If I raise the matrix A to the power R plus S, that's just the same as taking A to the power R times A to the power S. And I can associate those differently. So I can take A to the power R times S is the same as A to the power R, the whole thing raised to the power S. And we make a very special convention that any matrix raised to the power 0 is equal to the identity matrix. This is similar to in algebra when we talk about exponents, and if I take any number x raised to the power 0, we get a constant. So this gives us some extra properties for matrices. We want to summarize a bunch of the matrix arithmetic rules, just to, again, remind you, because these are important, you know all these. Matrices have to be compatible sizes for their operations to be performed. Matrix addition requires they have the exact same dimensions. Matrix multiplication requires the inside dimensions to be equal. So if A is m by r and B is r by n, then it's permissible because the inside dimension of r is shared, and the resulting matrix will be m times m in size. We have then a bunch of laws. We have the commutative law, addition commutes. We can also associate addition. I can add them in either order. Multiplication, however, is not commutative in general, but it is associative, so I can associate and do these in either order. And multiplication distributes over addition, and since addition associates, we can do this in multiple ways. Okay, some rules involving scalars in matrices. A scalar times the sum of two matrices is the sum of the scalar times each of the matrices. The sum of two scalars times the matrix is each of the scalars times the matrix. Two scalars multiplied by a matrix is the same as the first scalar times the matrix that has been scaled by the second scalar. And I can do a bunch of associations with those in different orders. Rules for the transpose. The sum of two matrices transposed is just the sum of their transposes. But the product of two matrices transposed is swapping the order of the matrices, reversing the order, and taking their transpose. Notice, if you want, you can be simple, and anytime you're going to take a pair of matrices and do this transpose operation, since A transpose, B transpose can commute, I can put them in a different order, I can say that A plus B transpose is B transpose plus A, and then you don't have to remember which one gets the special rule. Just always swap the two elements and take their transpose. Multiplying by a scalar the transpose doesn't change anything, and transpose is an omnipotent operator. A transpose gives us back A. Okay, so let's go look at a couple of examples. Let's take two very simple matrices and demonstrate that the product is not commutative. So just show that these two matrices don't commute when you go to take the product. So again, these are actually back, we already saw this example graphically. This is rotate by 120 and reflect around this axis. That's what this matrix does. Sorry, A rotates by minus 120 degrees. And again, if you're not sure, remember you can go back to your formula, cosine theta, sine theta, minus sine theta, cosine theta. So whenever you see a matrix that's got this sort of sine structure where these two numbers are the same and these two numbers differ only in sign. So when the diagonals have the same value and the cross diagonals differ only in sign, it's probably a rotation matrix or a scaled version of a rotation matrix. So this looks like it, and then you can show that this is 120. B here is a reflection around the E1 axis because this is minus 1. So again, we've already seen that this doesn't commute sort of graphically, but you can put these together and multiply these out, and you'll get one set of numbers, multiply them in the other order, rotate them, reflect, and you get a different set. Notice that these differ because here this diagonal is positive, here the cross diagonal is negative. Here the cross angle of the bottom. These are clearly not the same matrix. Okay, they have some relations, but they're not the same. Okay, and again, graphically, that was rotate and then flip versus flip and then rotate. And if you get confused looking at this diagram, and the reason, one of the nice things about this figure is it has this little extra set of claws at this end of the feathers, so you can track which way things went by understanding the relationship between those two. Okay, so finally then this video is just a bit long here. You might want to make sure you go through some sample problems. So again, these are sample problems just from the end of the book, but some of them will be straightforward. Construct a matrix that does this. Some will be questions like what does this matrix do? What does this word mean? Whether or not something is a rigid body or some other term we're going to have. Construct some projections. Compute some determinants. And maybe on the quiz, show algebraically some properties like distributive or associative properties. This chapter was chock full of words, so make sure what you should know. You've gone over all these words. If you look here and say, I don't know what some of those are, look them up in the book. Even if I didn't cover them here, can you see something here I didn't cover? There's a couple. I never talked about dyadic matrices. I'm not positive. Oblique projection was on the screen, but I didn't really talk about it. So you want to make sure you understand all those terms. They're all fair game for the quizzes and the clickers.